In the last video, I was able to wrap up the ROM control module cleanup and make sure that the breadboards were all tidied up. Today, I want to get into demultiplexing some of those signals and being able to group things together that really need to be mutually exclusive. Things like different registers asserting out onto the bus at the same time are going to end up being bad. I've done a little bit of this in the previous build. I need to carry this forward, but I also need to tidy it up a little bit. And I've got some decisions to make about how I actually want to go about implementing these in PCB. Today I want to try to get from concept all the way to schematic if I can. So let's jump right into that.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
Okay, you've seen this drawing in the background at the beginning of each segment. It's there not just to help frame what it is that we're working on, but it actually really is the high-level design of the computer that I'm working on. In here, I show 7 buses: address bus 1 and 2, ALU A and B, the main bus, a fetch bus, and an instruction bus. Now, the fetch bus and the instruction bus are kind of a bit of a misnomer as a bus in and of itself. It really only has 2 connection points, and it's really just a sender and a receiver. So we can remove those from our conversation today. The main bus is the one that's going to be responsible for moving data around most of the system here. Now, I have it hooked up to the memory. I've got it hooked up to the fetch register, all of the general purpose registers, and all of the peripherals. I'm anticipating 10 devices with both a data location or register and a control location or register. So that adds up to quite a bit. And I'm thinking I'm going to need at least 6 bits in order to address all of those different things that could have interest in asserting out onto that bus. Now, ALUA and ALUB, on the other hand, are far more whittled down. ALUB has 1 extra place that has interest. I probably am going to be pushing 16, maybe 18 things that might have interest in pushing out onto those 2 buses. And I'd rather not bump that to 5 bits if I can help it. So I think I'm going to artificially limit those to 4 bits apiece. Address bus 2 is similar to the ALU A and B buses in that it has a few things that have interest in it, but I believe I'm probably going to keep that limited to 4 bits worth of things that would have interest in pushing out onto that bus. Address bus 1, on the other hand, is relatively simple. There's really only 4 things that we'll ever want to push out onto that bus, and that is the program counter, the interrupt context program counter, and then the 2 respective return address registers. More on that when we get into interrupts. The last thing to call out is that I'm intending to be able to swap bytes in my 16-bit registers, and for that I've got a swap bus, which is really a pseudo bus. What it is a second entry point out onto the main bus that swaps the bytes. Now, to properly protect that bus, what I really need to do is increase the number of bits of data from 6 to 7 for the main bus. That should give me enough protection to prevent things from stepping on each other. Now, once again, as I'm recording this, I'm actually realizing things that were different than what I had set out in the beginning. So we'll see where this takes us. It's important to understand that I'm really not trying to find 128 things that I can assert out onto that main bus. But I'm definitely going to need more than just 64 of them, so I do need the extra bit in order to multiplex, demultiplex that many signals. Alright, so the next order of business then is to decide what types of demultiplexing, meaning how many bits wide, do I need to support. And it would seem pretty obvious based on the plan and what I defined as the bits wide that I need, but there's a caveat in here that I want to make sure that I call out. Well, let's call that 2 caveats. Address bus 1 only really needs 2 bits, but it makes no sense to put a 2-bit demultiplexer in there. I would rather go ahead and build out a full 3-bit demultiplexer and then tie the most significant bit low. That way I'm only ever dealing with the bottom 2 bits. Alright, well that's trivial enough. The 4-bit demultiplexers are relatively easily handled with the 138 series by tying 2 of them together and using that most significant bit as the enable. Each 138 has 2 active low enables and 1 active high enable. That makes it very easy to tie those together. The 7-bit demultiplexer, on the other hand, is going to be rather large, frankly, because ultimately what I need is a 4-bit demultiplexer, which then selects the appropriate 3-bit demultiplexer at the bottom. So with that, I will need to split the 7 bits into a 4-bit demultiplexer, the output of which enables the appropriate 3-bit demultiplexer at the bottom. I'm going to need 18 demultiplexers in order to handle those 128 signals. Now, once again, I'm not planning on using all those 128 different signal lines. I am going to design the PCB to be able to handle it, and I simply won't populate some of the ICs that I don't need. So that then gives me the plan. What's the other caveat, Adam? Well, the other caveat is that my plan is to have each of the signals be an active high signal. The 138 demultiplexer has an active low signal, so whichever one is selected is active low. Therefore, I'm going to need to invert that in order to get those signals shaped properly. And more than likely, I'm going to have to reinvert that at the module itself. Well, there is a 74HC238 3 to 8 line demultiplexer, which is functionally equivalent to the 138, with the exception that it does not have inverted outputs. So that shapes the signal the way that I want it going into the module, and I only need to worry about then inverting it on the other end. That's a good thing. Okay, so now I need to develop out for the emulator a 74HC238 IC. Okay, so this then is the newly minted IC for the emulator. It's frankly just a copy of the 138. The pins are exactly the same. The only difference is the outputs. So I had to change the initialization so that the outputs were all low, and then change this switch statement so that it made the outputs high, and of course default everything to low in the beginning. Very simple change. The next order of business here is going to be to reorganize each of these control signals. And at the same time, what I want to do is I want to make an effort to bring in every control signal that I can possibly think of and get this as complete as possible. Now, it's entirely possible I'm going to miss something, and I don't expect to have 100% accuracy here, but I want to make an effort to get as close as possible. I want to extend this out to be a total of 16 control ROMs. I believe that's what my upper limit needs to be. I don't know that I'm ever going to use all 16 of these, but I want to be able to write the EEPROMs for all 16 so that I've got them ticked and tied and set up and ready to go. That'll all fit into the 128-bit control word that I've got defined here. So that basically takes advantage of everything. And then I want to turn around and write out all 16 of those from 0 through F. My expectation is this has a good chance of breaking the build, which means that when I go about checking this into GitHub, the build itself may not succeed. And so I may have to spend some time debugging and trying to sort out the tests as well. Now, this will be a bit of a long task for me, but I won't drag you through it. I'll come back and show you the end results. Okay, let's just say that absolutely nothing ended up being in the same location using the same bit of the control word that it was before. Everything got moved around. What I tried to do is I tried to put the parts that needed to be demultiplexed in the least significant bits of each byte of the control word. So I've got here in control ROM 0, the asserts out onto address bus 1, and then I filled in around that. Control ROM 1 contains the asserts out onto address bus 2, and then I filled in around that. 3 is ALU-A, 4 is ALU-B, and what's going on up here, Adam? This is going to be used for the ALU and some of the logic things that take place. This is really 4 bits of the result of a logic operation between an A bit and a B bit. More on that when we get to the logic portion of the ALU. And then here's the big kahuna. This is the 7-bit assert out onto the main bus, where I've got all the different main bus asserts, and then I start in with a swap, protecting the main bus from having 2 things asserting out onto it at the same time. And it continues its way down. I do have 11 bits unused between control ROM 5 and 6. But then I've got loads, increments, decrements, writes, etc. all the way down the rest of the list through control ROM F, which is 16 of those. Could I move things around, reorganize some things, and make it 15 rather than 16 EEPROMs? Yeah, I could. But right now everything's grouped logically, or at least somewhat logically. And so I have the ability to find things in the control word a little bit easier. The next order of business here is going to be to improve the speed of this copy from the EEPROM into SRAM in the emulator. I do want to be able to conditionally do this if it's appropriate to do so, if I need that kind of testing. But I'm going to be in some tight cycles here that I want to have that improved so that I can get on to the more important stuff. So that's the first order of business here. Okay, I got that taken care of by setting up several conditional compiles. Specifically here, that if I am pedantically copying, I've got the old code. And if I'm not pedantically copying, then I have just a quick copy EEPROM, which happens from within the SRAM. It reaches over the border and performs a mem copy from the EEPROM into SRAM. Okay, that was easy enough. The next order of business is going to be to make sure that all 16 EEPROMs are represented in the emulator. Okay, that was nearly trivial to get that settled. I actually spent more time reorganizing the layout of the emulator. And the reason I did that is I want to keep all the control ROM stuff off to the right-hand side of the emulator. I wanted to closely match the way the physical layout is. And it's not perfect, but it'll work at this point. I did have to do a little bit of debugging because my control ROM signals when I was doing the rapid reset and just straight copying the data off the EEPROM into the SRAM rather than the pedantic copy. I had to spend some effort here making sure all of my signals got reset properly so that it would actually operate. So I spent a little bit of time working on cleaning that up as well. Okay, with that task complete, my next thing up is to expand out the emulator to create some submodules for demultiplexing each of a 3, 4, and 7-bit signal that needs to be demultiplexed. Okay, so here's the code for the emulator, and this is relatively trivial. Ultimately, what I have is a 74HC238. Now recall, those are active high, not active low outputs, but that's doing the demultiplexing for me. And basically all I've done is encapsulate this. So I've got an A input, which is being passed directly onto the emulated IC. B and C are the same. The outputs are literally going to be the outputs right off the IC. And then of course I've got my quote-unquote wire up, which handles all the signaling that's going to take place and an allocation of the components. The outputs are always going to be enabled, and that is because I always want to be outputting the control signals. So no matter what the size of the demultiplexed word is, I always want something to be outputting. Therefore, whatever is appropriate to be enabled will always be enabled. It gets a little bit more complicated with 4 and 7 bits. Now, this is an exceptionally trivial case. All I've really done is wrap the 74HC238 IC in some additional signals. As we get into the 4-bit and 7-bit, it'll become more complicated here. Before I go down that path and create those, I do want to turn this into a schematic that I can then copy and paste into other circuits. Alright, I'll step through this one relatively quickly. I've created a 3-bit de-multiplexer project in KiCad. This is for a submodule, and I'm really only interested in the schematic. Now, for this, I'm going to place a 74HC238 IC, and amazingly enough, they already existed. And then I'm going to also place ground reference and VCC. Now for my enables, I will be connecting the two active low signals up to low. I will connect the active high signal up to VCC. And then I've got, quite literally, inputs A, B, and C. And then quite literally outputs Y0 through Y7. Now I want that to be centered, and I want that to be centered. Now, why did I go about doing this? Because I'm going to use this just to simply copy and paste into other circuits. Next up, de-multiplexing 4 bits. The 4-bit de-multiplexer ends up being more of the same. It has 4 inputs, 4 bits of input, and then up to 16 bits of output. It very much is a copy and paste of the 3-bit demultiplexer, except I now have to tie the inputs together. The most significant piece of this is the most significant bit, which is used to select back and forth between the low 8 bits and the upper 8 bits. Let's put this onto a schematic. Okay, just like the emulator, I'm going to start with a copy of the 3-bit demultiplexer, and I really need 2 of those. Okay, 2 big changes. One is I need to tie this signal to D, and that signal to D. Okay, that leaves me with 4 inputs and 16 outputs. Okay, the 7-bit demultiplexer is actually more of the same, but on steroids. Up here at the top, I have a 4-bit demultiplexer, and I've built these using 74 HC138s rather than the 238s that are going to drive the final output signals. Now, why would I do that? Well, it turns out that the 138s are slightly less expensive than the 238s, and if I can save a buck or two, I'm going to save a buck or two. So, it doesn't hurt. There's no difference in the way that they function other than the polarity of the active signal. So I can tie the outputs of the top level of the tree to an active low signal, and I've got 2 of them on each of these 74HC238 demultiplexers here. Other than that, I've got 7 bits of input. The least significant bits are driven down into the lower ones, and those are so large that they can't be inlines. And then the 4 upper bits are driven into the top level, high and low 8 bits of the demultiplexer. As for the outputs, and I have each one of these outputs done in octal, and it just made it a little bit easier for me to number them as I'm going through them. So 128 of them. As for the wire up, again, I allocate and then I do the wire up, and the wire up's not terrible. And I'll be honest here, a lot of it was copy and paste and multi-line replacements. If I update A, I've got to update each of the 16 low-level demultiplexers. If I update B, I've got to do the same. If I update C, I've got to do the same. And of course, the first update has to handle all 18 of those demultiplexers. And that's basically it. It's like I said, it's just more of the same, a lot of copy and paste, but on steroids this time through. Next step is to put this into a schematic. Okay, we'll start with a blank sheet. Okay, let's start with the top level de-multiplexers. Recall that at this level I'm using the 74HC138s. Now let's do the lower level. These are the 74HC238s. If I'm careful here, I should be able to copy and paste some of the signal lines for VCC and ground. Next up, I'll hook up all the different signal lines between A, B, and C and the enable coming from the top level. Finally, we'll get the outputs labeled up. Okay, it's fussy, but it's done. Okay, for once, I actually got through everything I wanted to get through in a video, and it took less time than I anticipated. What do you say we take a few minutes and go ahead and populate out all the different registers that we need in the emulator? That will be all 12 general purpose registers plus program counter, stack pointer, and return address registers for both the program and interrupt context. 18 registers total. And here's what the emulator looks like. So I've got all 18 of my general purpose registers. Now these are program counter and the actual user registers. I've got my buses along the bottom, and then up the blank space in the middle right, is going to be ALU related things. And then I've got my control ROM logic sitting on the right hand side with some basic controls in the bottom right. Generally speaking, this is the form factor of the emulator, and I will work to get everything to fit into this form factor. Now, I still have some time. What else should I work on? Well, I have several things I still need to clean up related to my assembler. I've got a good dozen, I guess, or so items out here between bugs and things that I want to actually get done. So let me start with the bugs. I think the one on the top is an important one to start with, and it's related to the assembly directives and making sure that they all appear in the right columns. Seems to be somewhat important to me. Let me make some changes and get that cleaned up. Okay, well, I did manage to get those changes made, and I've got this committed and merged into my own local master repository, master branch. But if I come out here and look at the actual source now, I'm not liking the way that this is shaping up. And what I'm struggling with is a semicolon for the comment and a colon for an architecture directive. They don't mesh well. So in order to clean this up, what I'm going to do is I'm going to change the comments to be a / rather than a semicolon. Let me get that change done. And with all those comments changed to start with // that I think looks a lot more readable. The next bug to address is this one, and that is getting labels working with the assembler. Why is this a bug versus an enhancement or just something to get done? Because I believe I had it working at one point in time, and it no longer works. And you're asking, Adam, what makes you believe that you had it working at one point in time? The short answer is, I've got code for it, and the code is included in the assembler. But I really don't believe that this is working. And so I'm going to have to architect some tests and take a look at that and see what's going on. Let me figure out exactly what needs to be solved. I'll come back, I'll give you a rundown of what that is, and then I'll start working on it. All right, I ended up writing 4 very simple tests just to see kind of where things landed here with labels. The first 2 are jumps to just direct labels like entry, and then one is a backward reference, one is a forward reference, just to see if that would work. The next 2 use intermediates. Oh, well, what's the right term for that? I'm not exactly sure. But these are intended to be additional jump points within a function so that the actual label ends up being entry.1 or entry_1 or whatever that happens to be. Again, a backward reference and a forward reference. So how did these work out? Well, my first test here comes in with an unknown instruction. My second test, again, an unknown instruction. My third test comes up with an unknown character, so it's not recognizing the intermediate jump points. And this was a forward jump definition. Again, I've got an unknown instruction. So what to do about all of this? So I believe the concern ends up being in the find instruction function of the assembler. And it is looking for a constant value that can show up here. And what I need to do is double check and make sure that the allowed things that can show up for that constant value also include named labels. What really is a named label? Well, ultimately, when you distill that down in an assembler, it's nothing more than a number. That number could represent an address, or it could represent an offset, or it could represent just some constant value. And the key here is to make sure that I can recognize a named number and then ultimately replace that name with its representative number. So I believe that the ultimate is going to be in here to make sure that I actually get that working properly. Other than my tests up here that I just wrote, I've got a relatively clean working branch, so I should be able to work my way through this, and if I need to back things out, do that relatively easily. Okay, I'm going to take this on as an iterative approach, and this being the most trivial case where I am jumping backwards to a direct label, I want to see if I can't get this working. Okay, I think the first order of business here is going to be to take definitions like this and distill them down a little bit further. The machine code section is being pulled off, so that's not a problem. But I need to discern between the opcode and the opcode's operands. And in order to do that, I think I want to handle that in the scanner. I should be able to easily identify white space here, and then from the white space turn around and pass back any number of operands. Now, this is going to break the entire assembler as I start going through this, and it's not going to work again until it works again. What do I mean by that? As I start down this path, I have to actually complete it before the assembler's actually going to be able to do anything proper again. So this is a pretty risky move, but I have time in the video, but I don't necessarily have time in my life. So we'll see how this works out. This could be fun. What a rabbit hole that turned out to be. So I started working on just getting the labels working and ended up having to touch darn near everything in the process of that. And so I added in several things that I had queued up for some time as I was getting into things, and I do have a working assembler again, and I'm also able to create some of these intermediate labels .1, .2, .3 and have those work properly as well. But this assembler is trying to take on too much. It's really trying to be more than it really does need to be. And so likely one of my summer vacation projects is going to involve rewriting this into something that is distilled down to a purpose-built tool just for the 16-bit computer from scratch. Ideally, I would have wanted to retarget it, but it's just making it too difficult to maintain at this point. So what have I done? Well, on the left here, you can see that I've touched just about every component of the assembler. But I did create 4 new test scenarios, and this one is the more complicated one, which was a no-op and then a jump to entry 8. Here's the 8. This is wrong. That is being calculated incorrectly. I just noticed that. Alright, well, I guess I've got some more changing to make. Okay, that's fixed. Now this is rooted in the fact that I'm trying to do too much in this assembler. I need to distill that down to just the basics, just what's absolutely required. And again, I'm going to keep coming back around to this. It's getting unwieldy to maintain because its base code is not good. So look for that rewrite to come up at some point in the future. Well, that ended up being quite the rabbit hole. I'm glad I was able to shore up some of those things in the assembler. being able to jump to a location and being able to name that location is going to be increasingly important as I continue to build this out. Next step is going to be the schematic for the control ROM de-multiplexers, and that's going to be placed into a backplane where I can then drop the control ROM modules themselves right onto that, along with the control ROM control circuitry. Most of that's going to be KiCad work, and I'm trying to prep in order to be able to order PCBs from my supplier. We'll see you soon.